Okay, so good evening and welcome all of you to today's SET colloquium. The SET colloquium basically organizes the colloquia on the topics of interest in the fields of engineering, technology, software, medical, environmental, and also popular sciences colloquia. And this SET stands for Advances in Science, Engineering, and Technology. The colloquia are held at TIFR. These days, of course, virtual platforms on every Friday at 4 p.m. The two other colloquia that we have at TIFR, namely the Natural Sciences Faculty Colloquium that happens on Wednesdays at 4 o'clock, 4 p.m. And the Mathematics Colloquium happens at on Thursdays at 4 p.m. And today we have again a very just like we had a nice panel discussion last week on, of course, the corona and the origin of corona COVID virus. But this time we have another very equally or even maybe more interesting, as I heard this nice conversation between you two. And this is on the breaking the barriers, the hydrogen CO2 capture. It's a very important and contextual topic, and the triple helix model to achieve sustainability via ecology and economy. This is going to be given by a very distinguished speaker today, Professor Ramakrishna Sonde, the visiting professor at the Department of Chemical Engineering at IIT Delhi. I said, of course, would like to thank Vivek, colleague Vivek Polshetwa, for making this talk a reality. So without taking more of your time, let me on behalf of all of you invite Vivek to introduce today's speaker and also conduct the rest of the proceedings. Vivek, thank you.
Yeah, good afternoon, everyone. I think it's my honor to introduce Professor Ramakrishna Sonde. He is currently a visiting professor at Department of Chemical Engineering, IIT Delhi. Professor Sonde started his early career working as a scientist in Baba Atomic Research Center, Mumbai. In the formative part of his career, he was deeply involved in nuclear energy research, developing technology on heavy water plants. He then completed his PhD during his stint at Atomic Energy Commission, AEC, in the field of isotope separation, simulation sciences. He was awarded for his contribution to nuclear energy and science, a gold medal during the Golden Jubilee Award in the hands of then Prime Minister. Subsequently, after 23 years of working in atomic energy, he was invited to join as an executive director of National Thermal Power Corporation, NTPC. During his stint there, he created a new institution called Energy Technologies, which is now renamed as NETRA, to develop technologies in the thermal coal sector. He then worked as an executive vice president and the member of the executive council of Thermax. He is currently the chairman of the task force constituted by Niti Aayog, Government of India, on the production of methanol using high ash coal. He is also a fellow of National Academy of Engineers, a member of the CII FICC Consortium for Power and Renewable Energy, a member of DST Committee on Water and many other committees. He is currently working as a visiting full-time professor at IIT Delhi, adjunct professor at IIT Jammu. He is also advisor to CSIR NEERI and a principal scientist at SWM company on circular economy. And recently he joined us as an advisory member to a newly found CO2 India network. With this very brief introduction, I kindly request Professor Sonde to deliver his colloquium.
Thank you, Vivek, for a generous introduction, and thank you, Professor Satyanarayana, for asking me to deliver this. It's a double kind of a privilege for me to talk to your scientists in TRFR as well as on a topic which is very close to my heart, very close to my heart. So I begin my talk, but I'm sitting in my residence because I didn't go to office today. Delhi is sizzling at about 42 to 43 degrees. So I'm more comfortable at my home with my air conditioner, but we are on the flight path. So there may be occasional kind of interference because of the big flights, big planes flying on my head. My request to all of you that if you can switch off your, mute yourself so that whoever wants to interact can be switching it on and then we can interact. I would take, I think, as per what Vivek told me, about 45 minutes of this particular talk, and then we will open it for question and answer session. Is that right? I mean, that's the way that I thought I planned, but 45 minutes to 1 hour that I can go, but depends upon the kind of an interest that I would like to have more of a later on a conversation and a question and answer session. So as you would have guessed, and this is something which I am deeply involved is this climate change, and we have realized where are we and what is the challenge that we are facing with respect to carbon and hydrogen, and how do you actually now break this bond between carbon and hydrogen but still keep them together is a challenge that we as scientists and engineers are looking at it. So that's one of the major problem. And why I'm saying this boundaryless triple helix collaborative model, because the problem is so vast, so deep, and so much requiring and multiple disciplines to come together. I'm convinced that if you want to solve this problem in every sense of the word, then only the global collaboration will happen. I come from atomic energy when India started our work, and I was involved in developing a technology PHWR. And the way we could develop the technology is by simply collaborating with each and everyone, big company, small company, research institutions, academic institutions, whoever is willing to do that. And I also feel today that, we can't work in silos. It is requiring a tremendous amount of what I call a triple helix, what I call a golden triangle, where multiple institutions, the academic institutions, the research institutions, and the industry must come together. And that is the model that I'm proposing. Now, this is a familiar subject to most of you, but I do not know the cross section of the audience. So I just want to go little basics before I come into the deeper and deeper aspects of this so-called carbon management, climate change, and carbon dioxide. So if you can see this chart here, y-axis is the gigatons of carbon and x-axis is the years. This was me and Professor Paul from Princeton. We developed in 2004 when I was invited to lead this particular India's climate change during the Kyoto Protocol. I'm talking about 2004 to 2008, where those, tumultuous years when India was struggling, India's energy requirement was going up. Even now it is going up exponentially, and this climate change was staring at us. So we had created this particular plot which showed that, the stabilization triangle, what I call here, right now when you're talking about 2021, we are close to that tipping point. And as you can see here, we are here, and anthropogenic, that is the CO2 coming from the human activity, is now at a rate of about 40 gigatons. I mean, it's about 38 or 39, but you can take it as a 40,000 million tons or a 40 gigatons of carbon dioxide is emitted. This is a carbon, and carbon dioxide is whatever you multiply 3.6 between the carbon dioxide and carbon. So what is happening today, friends, is that, we are at a point where the concentration is going beyond 410 ppm. In fact, when we did the modeling in 2004, we thought that 412 ppm will reach in 2030. And we are actually, it is a shocking that today, when you look at those golden standards, which is in Loa Moa laboratory in Honolulu in Hawaii, where actually a carbon dating and CO2 measurement are done. Today it has reached about 413. You can get that on your live link. What is the concentration? We have advanced the concentration by 10 years. So with all this thing going on, renewable energy and efficiency and so many things, the fact of the matter is that the carbon dioxide increase is taking place. The climate is changing faster than what we know. The extreme events are taking place. The tornadoes, the heavy rains, the issue of glaciers melting, all those telltale indicators of climate change is happening at a faster rate. If at all the climate change, the carbon dioxide concentration has come down only when the economic activity has lowered, like in 2008, when economic activity had collapsed because of the Lehman collapse in US, or during the Corona, it showed that there is a little bit of a dip in the carbon dioxide concentration. Otherwise, carbon dioxide is on a hockey stick, and therefore it is shooting out. And you all know that 470 ppm is a tipping point when the temperature will cross 2 degrees centigrade. And all of you are fully aware of this tremendous challenge of what we call about the 2 degrees centigrade tipping point, which can really kind of create a havoc to all parts of the global kind of a thing. So I'm not giving a gloom boom kind of a thing, but I'm just giving you a reality that the need for an action is right now. And if you take some action, whatever we talk about net zero, And how do you reduce this 40 gigatons to 0 gigatons? And that to do in next 3 decades, 30 years is a tremendously tall challenge for all of us in terms of meeting this. So if you now look at it, I'm just giving you a reduction strategies. Net zero, if you want to reach by 2050, and you take many scenarios. So I will come back to what is the scenario. Right now, I'll not tell you the scenario because that will be too many things to be putting before the horse. So I'm just saying that let us, if you are now talking about, I mean, suppose if I reduce, let us say with all the strategies that is available and the COP25, if you reduce by 2% every annum, that is what is happening. Currently, we are reducing our CO2 emissions by about 2%, and the rate of growth is more than 3%. So in effect, CO2 is increasing and not reducing. But if you are able to net bring it down by 2%, then you will realize that your concentration will go to about 550 ppm. And it will be much higher. It will cross the 2 degrees centigrade threshold value. If you now bring it down by 10%, 5%, it will go to 500 ppm by end of 2050 in 3 decades, which will be for many of you in the audience, you will be your active career life. You will be seeing that we are actually crossing the threshold value. The third scenario is that maybe next 10 years, we work on a 5% reduction strategy. And after that, we increase the rate of reduction to 10%. Then you will realize that maybe that is the strategy 480 degrees centigrade will reach, which is just below the tipping point, which is probably what will give a existential crisis or existential danger of the earth itself, or our human beings as a species probably will be maintained if we are able to follow this trajectory number 3. And of course, the trajectory number 4 is if you are able to do by a magic multiple technological initiative, if you are able to bring it down by 20%, 20% every year from now onwards to 2050, then we will really reach 2050 is net zero, because every country, 185 countries are committed. And in October, when there's a COP27 happening in Glasgow in UK, all of us will be again committing that we are going to be following a net zero by 2050. And if you want to do 2050 net zero, then you will have to really reach this number of 20% per annum reduction. So remember this, 2%, 5% is not okay. 5%, 10% is one strategy that I'm going to be presenting to all of you. What is the strategy which will actually enable us to reach this particular pathway? And 20% is a real, if a human intellect can bring out what is the way that we can bring down by 20%, probably that is what is going to be savior for this particular thing. But if you look at this 2% to 20%, and then you add the carbon capture, this is a reduction. Reduction can happen because of the renewable energy. Reduction can happen because of the efficiency. Reduction can happen, but if we are able to capture now carbon dioxide, then you will realize that we have to capture almost for this scenario. If you read this scenario of 550 ppm and you want to still capture, you have to capture about 886 gigatons of carbon dioxide. And if you follow this particular strategy, you have to capture only 199,000 million tons or 199 gigatons of carbon dioxide to be sequestered. So please, I just want to give you the magnitude of this carbon dioxide. Today, if you weigh the human beings, whatever we are close to about 7.2 billion humanity that we say as a Homo sapiens, and you weigh them together, our total weight is less than 600 million tons. And the carbon dioxide that this humanity is consuming is 10,000 times more than what the total weight of organic mass and water and the other bones, if you add, our total weight is about 600 million tons, and we are actually generating 40,000 million tons of carbon dioxide every year. And that is where the entire, our whatever that we say that, you know, we have created many things, many revolutions, but end of the day, what we have done is we have sucked the resources of the globe, and we have created this monster of carbon dioxide, which is now staring us at the back. So we have double challenges. One is reduction of yearly emissions, and then finding out a safe storage place for such a mega quantity of carbon dioxide. Many times they say, oh, let's convert it into polymers, let's convert it into some solvents. But these are all going to be very, very minor fraction of what is coming out into the atmosphere. So you cannot, you cannot say that I got some magic wand where I can convert the carbon dioxide into some chemical or some solvents or some lubricants or some product into the food and beverages. So it is very clear that this problem. So I know that all of you know this, but I wanted to reinforce that the time has come for action now, and this is the challenge that you are talking about. Now, one point that I want to really handle it here, that everybody is blaming it on fossil for the climate change. And undoubtedly we say it is because of fossil. Fossil got created over about 2 million years when antimicrobial activity and solar created this kind of a what we call crude oil and natural gas and coal and all those peats and lignites and what have you. And we are now saying that fossil has been responsible for this particular dangerous situation that we have landed in. But if you really look at it in reality, we are in this jam, and I want to repeat this because many times we blame the instrument which has helped us to develop, forgetting who has created that instrument. That we are into this jam due to the way the fossil technologies were developed and promoted as the success of industrial revolution. So, my dear friends, you have to clearly realize that cheaper energy, just to ensure cheaper products to fuel growth, has caused this particular thing. I just want to alert you or make you aware of the fact that it is not really the fossil fuel, but it is the way that we actually exploited the fossil fuel which has landed us into this problem. So all the production processes were based on principle of guzzling carbon dioxide emissions. Because if you go to 1900s and 1920s, all the technology which was discovered and trumpeted as human intellect or humans kind of a innovative or a creative nature, it was because of discovery of what we call the steam Rankine cycle for conversion of fossil energy into electricity, and an internal combustion engine which is converting the fossil energy into a traction power. So these were the two engines which actually fueled the entire amount of the growth, and whatever now we talk about the $60 trillion economy was based on these fossil fuels and making fossil fuel energy cheaply available to the industries. And that is what we were very, very proud that this is what we have done. And we have forgotten that these engines, which were crown jewels in the human invention, Carnot cycle and Otto cycles, were just about 30 to 20% efficiency. And because of this, actually we have gotten into such a particular jam today of a 40 gigatons of carbon dioxide coming every year from the way that we have designed the energy conversion system. So many times in the many dialogues at a higher level, that we stop fossil. Let's go to renewable energy. It is not a switch. It is not a switch that on tomorrow morning on 3rd of July, I switch it from a fossil to a renewable energy. Fossil is so ubiquitously now has gone into all of us in every art. It is not possible in every action. It is not possible that we can change it tomorrow. It will take a long time. But we simply don't have time to switch, to kind of remain with fossil. So what do we do? So it is the greatest challenge to the humanity. I think if you talk about three challenges, one is climate change, one is artificial intelligence, and if you talk about the third one is what you're talking about, this kind of a viral infections. If you take these three as the greatest challenge for the survival of the humanity, climate change is at the very top. And if you're talking about the climate change, the reason is that we have taken the genie out of the bottle and now we want to put the genie back into the bottle. And in this is a global question. Yeah, you have understood that globe has to be collaborating, because whoever may be now emitting CO2, it is going to democratically equalize the concentration everywhere in the world. So you cannot say that I'm not responsible for somebody else's action, or my actions will not impact somebody else's action. So this is a true, when you call a Vasudhaiva Kutumbakam, I think this is the true sense of a climate, CO2 trying to kind of bring an equity in all the climate. So how do we now handle this particular genie? The debate on who is responsible, is there equity? This all I know. 2004, we had two. We said that we and China said that we are not responsible for this this climate change, and now we want more energy, we want a cheap energy, the same energy which has fueled your development, we want to do that, why are you stopping us? So those were very hawkish dialogue that I was a part, and I now start feeling guilty that those dialogues will not help today. We have to find a solution, a global solution, which is scientific, technological, strategic, financial, and survive. Indeed, a complex problem. So I just want to tell you, my dear friends here, that the way now from a energy, from a primary source, which is a fossil energy, to the consumer, the amount of efficiency that we get when I multiply every efficiency, there's a Carnot engine efficiency, there's a transmission efficiency, there's the end conversion efficiency, whether it's for air conditioner, for a lighting, or any one of the devices, you will realize that the overall efficiency is 14%, which means that it is that about out of 40 gigatons, 36 gigatons is avoidable carbon dioxide. And 36 gigatons we have been spewing out for last 100 years. And now we are blaming fossil fuel and not realizing that we adopted a non-sustainable pathway. If only we had adopted a better pathway, we could have actually avoided the danger that we are currently in while meeting the energy requirement. Options were available in 1890 when steam Rankine cycle was introduced. In 1910, when famously Ford wanted to avoid the horse shit in the New York streets, and he said that he has developed this automobile, we had an option to do that particular thing. Today, when we talk about the e-mobility, or when we talk about many other ways of conversion, which is what I'm going to be talking towards the end of my talk, is very clearly saying that entire thing, we actually got into this jam because of what we call the issue of economy, because economy is so much governing that many times we as scientists have to completely surrender to the aspect that that economy controls. And that is something I feel I must want to leave this particular thought, because today what has happened, many big energy companies, I don't want to name them, the many big companies do not have built so much of $1 trillion wealth from a fossil fuel, and therefore they don't want to actually abandon their technologies, their $1 trillion investments. And because of that, we are continuing to do the less efficient technologies will continue to be running. And now we are saying that the only solution is that we have to sequester it. So please understand this aspect very clearly. So let me take an example of a power station which provides even now more than 76% of the total electricity in India. And you will realize that though per kg of carbon coal, you should have delivered 7.7011. But in reality, the carbon dioxide coming out per kilowatt hour at the user end is almost 2.2 kgs of carbon dioxide. So again, what I'm saying is that yes, carbon is responsible, but the way the carbon energy conversion devices that have been adopted in the society for last 100 years has been the root cause for this problem. It is a total human irresponsibility of using a low efficient system, which is caused where we are. And this is a thought that I want to leave it with you before I talk about the important aspect about now what do we do? Okay, we have understood the problem. What do we handle this? So clearly, as I said, that we have to go back to the high efficiency cycle. I mean, this is absolutely important that as you increase the efficiency per kilowatt hour, the kg of carbon dioxide emitted is going to be reduced. So that is the pathway that we have to follow. And India, I mean, I'm saying that we cannot talk about a sequestration because many of the developed countries having reached a developmental plateau where they grow only at 1 or 2%, where India has to grow up about double digits, about 10 to 12% to reach at least $5 trillion economy. You will realize that we need to follow this efficiency pathway, and only residual carbon dioxide can be sequestered. And that is the strategy that I'm proposing to India. So whatever that we did for last maybe 70 years have been only incremental efficiency increase. And this will not do. This kind of a incremental efficiency from a subcritical to a supercritical is not going to meet the requirement of reducing the carbon dioxide. If you want a 2%, you follow this path. But as I showed in my first plot, if you want to reduce carbon dioxide, you've got to reduce at the rate of minimum 5% for next 10 years and 10% thereafter. That is the only sustainable pathway. And these kind of 2% pathway of simply going from a subcritical to supercritical, though India is following this pathway because some Western countries have followed it, will not do the job. Similarly, even in the target wise, if you talk about the direct air capture, because air capture, when you want to do it, 60% of the industry, we need to set these targets, and those targets should be substantially higher. So the approach that is espoused, I'm not, my approach, I'll come maybe 10 slides from now, I'm going to give what should be the approach. But right now, there is a kind of an agreement that, the globe has built a huge assets using a fossil fuel, which are low efficiency. So we can't abandon them. Definitely, they say that we can't abandon. I have a question mark whether why can't we abandon them? But let's assume that economics, whatever stupid it is right, and therefore we cannot abandon those assets. And what we can do right now is capture carbon dioxide from these plants and then sequester them. So that seems to be one strategy that we followed in 2004 to 2010, and we called it as CCS technologies. In fact, sequestration, many of the non-chemistry people did not even understand what is the sequestration, what exactly is the theory behind sequestration, but I'm not going there. I think this learned audience understands why we call it a sequestration and not a storage, because you got to mineralize carbon dioxide when you take it to a supercritical level. But then this would increase. Obviously, when you do this, there will be an increase in the cost. 20 to 50%. Today we know when the petrol costs us 105 rupees, and all of us, though we love nature, but when it costs 105 rupees, there's a huge amount of, I don't want to go to the economics and politics aspect of it. So the problem is that when you want to capture carbon dioxide, this would increase the cost by 20 to 50%, and hence it is not economical. Hence, what the global community did, which is what has caused, throw economics in this, and hence use this captured CO2 to generate more oil and gas and call it as enhanced oil recovery. So what is done in US is that, okay, you capture and use that carbon dioxide, put it in Texas, all the oil wells, and change the viscosity, because CO2 has got a super solvent properties in that particular 77 degrees and 77 bar and 29 degrees, and get your enhanced oil recovery. So this is what you have done. Can you understand the stupidity of this situation, that you're using CO2 to generate oil, which generates more carbon into the atmosphere? But still, because you're getting an oil, and oil is having a value, so you are doing a zero-sum game of capturing carbon dioxide and recovering this 20%. So the situation of sequestration is that you must sequester it. Don't use it for enhanced oil recovery. But when you sequester it, it is very important that sequestered CO2 remains in the earth for a long, long time. This is one message, because when I was a part of the global group on carbon sequestration leadership from CSLF, and a lot of papers were published in Nature and Science, we have realized that only in those areas where there are good sedimentary rocks with equally good cap rock is only ideally suited for carbon capture and sequestration, and where the population density is sparse. A country like India, 16% population, 2% land area. If you store that carbon dioxide, you don't know what kind of a seismic activities will create a huge challenge to the population. Leave alone, the carbon dioxide may not remain if you don't have a good basalt, because we have got basaltic rock, but basaltic rock is not good. And I'm not getting into the geological aspect, because that itself is a separate topic. But what we felt is that, do we agree in the globe that to move CO2 from one geography to the other geography and store them at a global scale outside national boundaries? So one of the things which I had to propose during that time is that, look, there are 6 good sedimentary rock, one in Norway, one near Norway, one in near Germany, one in Australia, one near Singapore, and one in US. So if those good rocks are there, which can easily take about 800 gigatons of carbon dioxide, can the CO2 generated and captured in India or every country, can you use those places to actually find a permanent burial for sequestering carbon dioxide? I'm going to raise this topic again in the coming discussion, because we have to come out of this not in my backyard mindset as far as CO2 is concerned. So nationally, CO2 can be converted. Otherwise, that's what me and that's why Professor Vivek, we are trying to do. Is that okay? If there's one pathway, if not, can we find a resting place by conversion into a product and fix it as as a chemical, which is going to be very small fraction, but convert that into a fuels like a EOR, like you are getting EOR there. Can we get now a carbon dioxide converted into fuels? And I'm going to be talking towards later part, lot of things on that conversion, because that is where big science is happening. That is where the really exciting science is happening. I think all of us as scientists are excited that if this is not possible, if this is challenging, can we find out a pathway where carbon dioxide can be converted and fixed in a terrestrial mode rather than in a geological mode? But my feeling is that we cannot completely abandon that. We would need about 50% to be stored geologically at, under the sedimentary rock, and 50% may have to be converted into carbon capture US. So changing from a carbon capture and sequestration to a carbon capture and utilization sequestration are the two clear pathways that we have to do it. You can see here, I have seen this Slipner that is in North Sea. Wonderful. I mean, this is one area where you can store maybe globes 30% of the carbon dioxide in that sedimentary rock. It is like a God-sent thing. There's a cap rock. There is a mineralization. There are a lot of alkaline materials where you can convert it into. So there's a Insala, there's Snowit, this is in Germany, and then there are another three which can be used here. But all this thing here where you talk about oil and gas fields, enhanced oil recovery, coal methane, and that they will really not do a GHG mitigation, though this has been touted by some of the scientists as another way of finding a carbon and getting a value, because you are able to get more hydrocarbons by putting carbon dioxide into a rock where there is the oil which is present. I personally would not recommend this pathway, but this pathway is a better pathway. But only point is that globe does not have, every geography has got can afford this kind of a sedimentary rock. Certainly not in India, because our geography does not allow, because of a nature of the whole system here. Now, coming to let me talk about the science part of his carbon capture and sequestration. This is a three-point triangle, my dear friends. There's a capture part. Capture part can be done in a pre-combustion mode, during combustion, and a post-combustion. So whatever now currently, whether it's a steel plant, cement plant, fertilizer plant, power plant, utility plant, now what we have to do is that the plants are already available. We can't change the technology. That's what the economists tell us, though I don't agree. But let us assume that those assets cannot be closed tomorrow. They may be able to be retired maybe in a decade from now. And that is what the strategy that I followed, that we can remove this carbon dioxide from the existing emissions, but go for a higher efficiency, which is a pre-combustion. I will explain this a little later. So there's a post-combustion where tremendous amount of R&D is required. So if one thrust of R&D, and especially since I am addressing to my friends in TRFR and of course many other basic research institutions, and that is where the CO2 network we are talking, where our Vivek is leading that effort, is advanced chemistry plays a major role. It's an excitement for the chemist, not only on the conversion, but on the capture side. I'll come to that a little later. Then, of course, the carbon dioxide transportation, cryogenic transportation, or a supercritical transportation, and the sequestration. So all these three things will take about 20 to 50% penalty on your cost of energy generation. Today, if you are getting a power at 5 rupees, your power in your homes will become 20 to 50% more, depending upon the technology that we're going to be putting, or somebody should pay for that carbon dioxide as a carbon tax. So I'm not putting too many economics into this discussion, knowing the background of all of you, but I'm just saying that this is entirely doable, and you can capture it, you can transport it, you can sequester it. I said sequestering, it should be a global sequestration. It is not possible that everybody has got in their backyard a comfortable a geological rock where you can sequester carbon dioxide. So this is the three-point triangle. And when you do that, today's technology, I mean, as of I'm talking about yesterday evening, whatever technology, you'll find that the removal of all the SOx's, NOx's will consume about 0.1 kilowatt hour. Capture today, whatever technology that we talk about, I mean, I will go a little detail later on what is the technology, 0.5 kilowatt hour and pressurized 0.5. So what is happening is that the carbon dioxide, which is generating energy, which every kg generates, let's say 1 kilowatt hour, will now consume 0.7 kilowatt hour of energy in doing this three-point triangle. That is the purification, capture, pressurization, and then sequestration. So you will realize that the net energy which will be available 0.3 kilowatt hour. So can we have any magical process which is where we can actually bring down, that means from a 0.7 kilowatt hours, can we bring it down to a 0.1 kilowatt hour? And that is what you as scientists, all of us have to really work at, that we don't have to really go through this, to purify it, partially pressurize it, then capture it conventionally through a amine, and then you amine using a steam, which is a huge energy guzzler, and then go to a high pressure compression and sequester. Now, this all takes almost 70% of the energy otherwise generated by carbon dioxide. Do you have a magical process where you take carbon dioxide, you take water, you put some earth abundant material and do some magic in this in this box, and we'll come back to that magic. And that is where what I call the tremendous amount of challenge that is resting in the multi-science discipline. And that is where I'm talking about my triple helix model, because if you're able to come up with this, and I would like to assure you all of it, that there are these processes available, going away from what I've indicated earlier, the process of this, we can get into this kind of a process, which is going to be the only way, which can consume only 0.1 kilowatt hour, which can then make carbon capture and sequestration completely viable as a technology and a viable technology. Now, capture and from point sources, when you talk about capturing carbon dioxide from a stack that you must be seeing every day, whether it's a power plant or a steel plant or any other chemical plant industries, which is spewing, as I said, 40 gigatons of carbon dioxide, 40,000 million tons, because gigatons sometimes, so 40,000 million tons. The problem of this capturing, one is of course a direct air capture, but even from a point source, that there's a pressure of carbon dioxide is very low, and therefore it puts a lot of energy. There are high temperature, again, it is having a problem. Then there is a SOx, which is present because most of the fossil fuel contains sulfur. So while you're getting CO2, you also generate SOx or hydrogen sulfide. And that is again a highly corrosive and a toxic thing. You need to remove it. And that is again a challenge. NOx is again present. So NOx gives a lot of problem. And then of course, you're talking about the oxygen in the gas, fly ash in the gas. So when people are doing a lot of research on carbon capture, I keep telling all my research friends that don't look at carbon dioxide capture from nitrogen and carbon dioxide or water and look at your thing. That carbon dioxide contains a lot of contaminants like SOxes, NOxes, particulate, mercury, oxygen. And unless you remove them, or unless you've got a magical process, the cost of carbon dioxide, whether it's going to be physical separation, chemical separation, advanced separation, biological separation, hybrid separation, or a cryogenic distillation, is going to be tremendously energy consuming. And whatever energy that you are getting it from a fossil fuel, if you're going to be consuming mostly to capture it, then I think you are into a zero-sum game. I mean, just to tell you what is the current state of the art, using your, I mean, all of you knowing, so I'm not getting the process details, and you find that there's a stripper, and stripper using a steam, and it consumes about 1.5 to 1.6 tons of steam per ton of carbon dioxide stripping. So 1.5 tons of steam, and carbon coal can generate maybe about 2.5 tons. So 1.5 tons will have to go, almost more than 50% of the energy will go for stripping the carbon dioxide. Then what is the fun in capturing carbon dioxide? So though amine process is treated as one of the well-proven process, what is missed here is that how do you strip carbon dioxide from amine? Which means that we have to go away from amine, or we have to actually do a lot of changes to the amine molecule. And that is where, a lot of work which is happening on the basic chemistry and solvent adsorption, sterically handed modified amines. I'm sure some of you may be working on this 2-amino, 3-methyl, 1-propanol as one of the major changes. So there's a huge rush for developing a solvent which has got a right kinetic and equilibrium absorption, selectivity for acidic gases, and it manages the degradation, because some oxygen will get past even if you have to remove all oxygen coming out of your combustion process. So this requires definitely new R&D directions. And therefore, again, I'm not getting into from a primary amine to a secondary amine to tertiary amine, and the kind of properties which are looking at it, assuming that a liquid gas contact systems are the best compared to any other adsorption or a zeolites or a ionic liquid, which are very expensive. A lot of options are there. I'm not saying one should not look at it, but there is a tremendous amount of scope for making those modifications. So now I come back to the strategies that we need to look at it. So one, I still feel that we have to abandon, or we have to start closing these assets which have been built on a poor efficiency of a steam Rankine cycle. I think time has come now in this decade to look for new energy generations. And that is where, my dear friends, this fuel cells, the electrochemical conversions, and many other changes going to hydrogen becomes a major challenge. This is my real mission now, to actually take out the current state of the art technologies of energy conversion, whether it's for refinery, whether it's for fertilizer, whether it's for steel, or whether it's for power generation. Can we go back to a higher efficiency trajectory while remaining in fossil? Or can we abandon fossil and go for a renewable energy? I'm not saying that this is either or, it is or and. That means we have to go for a higher efficiency. We have to actually increase our renewable energy portion in our energy mix, and then of course develop a CCUS. So when I'm talking about this 5% and 10% trajectory, which will allow us to avoid this 2-degree threshold and bring down the concentration to under 460 ppm. 460 ppm is still a dangerous concentration, but still it will not create the kind of a havoc the human beings and all of us can develop a adaptation process to take care of that 460 ppm. Right now we are at 412 ppm. So in next 3 decades, if we are able to arrest that concentration under 460 ppm, we will need all the 3 trajectories. One is higher efficiency trajectory. Please keep it in mind, my dear friends. This is very important. I am working on this. I'll give you some glimpses of this. How do we now improve the renewable energy? I think there's a tremendous amount of scope to get into the renewable energy and then develop a CCUS integrated. So I'll take now next 10 minutes to complete this and open the topic for a question and answer session, because I think I need to hurry it up now in terms of my this. So from an older strategy of a low efficiency system, I am proposing that we should now go for a hydrogen-based water electrolysis, hydrogen coming from coal gasification, hydrogen coming from steam methane reformation, hydrogen coming from biomass, and we are working on this particular hydrogen, and hydrogen as a distributed energy, which is a carbon-free energy coming from thermal to electrical to traction. So when you do that, you will realize that 90% for the renewable energy fossil fuel, 75 to 80% for getting hydrogen from water electrolysis or from the coal gasification, and 75% as a combined heating and power. So you will realize that from a 14% trajectory, which is what currently we are utilizing energy, there are some marginal, as I said, a percentage, 2% improvements are happening, getting LED lights or supercritical power plant. We are doing something on the energy efficiency, but this is a very different pathway. If we're able to go not a combustion pathway, that means we don't go through a steam Rankine cycle, then you can really get an overall efficiency, which will be almost 3 times more than what is this. So my first strategy is to develop all the technologies, the basic science which is required to abandon this process and go for a hydrogen base. And I'm glad to tell you that a lot of big companies, I don't know to again name them in India, public sector, private sector, are actually, it is very nice that at a very high level, at the chairman level, are realizing that now is the time they must look for these new efficient technologies. That means we are not taking fossil out of the equation. What we are taking out of the equation is the conversion efficiency, which we are boosting it from a 14% to about 50%. And I think many of you may be knowing, as I said, I've spent last 5 years in developing a fuel cell onboard reformer. We have developed a high temperature proton exchange membrane cells along with the CSI laboratories. One of the showcased project, in fact, we dedicated to the nation what we known as the polybenzoimidazole based membrane electrode assembly and the whole aspect on fuel cell. Again, this talk is not on the fuel cell, but this is something which is going to meet the requirement of a high efficiency power generation, and balance of the heat can be converted for heating and cooling. And at a 75%, even at a kilowatt, I don't think in the globe there is any device which can match the kind of a conversion that we are building using hydrogen or the hydrogen carriers like methanol, ethanol, and methane. So theoretically, I don't know to go. Fuel cell is the new thing, because it gives you 94.5% efficiency. So from a Carnot efficiency, which is lower at this range of 400, about 30-40%, you are able to now hit about 70% efficiency using a fuel cell. And therefore, we have to go for a fuel cell as a high efficiency. So the next one is, of course, as I said, carbon capture and sequestration. Sequestration, wherever sequestration is possible, it has to be a global sequestration and not a national level sequestration. But on the second term, that is carbon capture and utilization, can we actually, what is the best pathway? And that is where hydrogen becomes an important role. So carbon capture, therefore my title of the talk was carbon and hydrogen. Hydrogen is the one now magical element that is available for me to actually tame carbon dioxide and capture them and terrestrially sequester that carbon dioxide. And all of us are excited because today, when you get your renewable hydrogen from water electrolysis, and then you are able to actually reduce, because that much energy is available, and you can reduce your carbon dioxide and marry carbon dioxide with hydrogen, you get your production of fuels and chemicals. And therefore co-electrolysis becomes one of the major thing. I said about a magical process earlier, carbon dioxide and water and the ambient condition, but I don't know what is that magical process. Some of you should work on that magical process. But what process Professor Sonde knows is co-electrolysis. So I work like a fuel cell, a reverse of a fuel cell, where what we call solid oxide electrolysis, which can actually convert water and carbon dioxide into a synthesis gas and give me synthesis gas. I can make many products out of it. And that is where we are looking at CO2, take water, send it to a solid oxide electrolysis, synthesize it. And this can be synthesis, can be again, need not done on a copper zinc, which is a traditional transition metal operating at high temperature and high pressure. We can do even this synthesis at an atmospheric condition. And today, thanks to the material science and thanks to the chemistry and thanks to the density function theories and molecular engineering, has allowed us to find out, explore many new pathways. I'll touch some of them in my path and get this. So this becomes an important pathway. Solid oxide electrolysis is something which we are trying to build for the nation, where you can see the kind of efficiency that you get for hydrogen is almost 30% higher than conventional, and therefore it becomes one of the best way to get your process. Now, CO2 fuels, one is, of course, as I said, via co-electrolysis, but then one has to look at it, what is the energy and how can we really improve it? So what option that I've got, if you give me hydrogen and carbon dioxide, I can convert it to methane, I can convert it to methanol, I can convert it to ethanol. What is the best pathway? I don't know. I mean, you have to now go into selectivity engineering. My dear friend, that's been one of my, when I looked at the isotope separation, my atomic energy days, we were looking at how do you select a particular isotope, and we had used tremendous amount of new methodologies, new process synthesis, and looking at this whole aspect about how do you reduce carbon dioxide. Now, this is another topic, given my time that I have to complete in shorter time. I'm not getting into the details, but when you look at the RHE, the reduced hydrogen electrode versus the electric density, you understand the classical conflict that you are going to be having. And therefore, when you want to go to a ore potential nearly zero, then you will find that your flux has come down to zero, and therefore carbon dioxide reduction becomes a major challenge. I mean, I'm sure the Hess's curve is known to you all. So combustion energy delivers 9.1, but we need about 18 kilowatt hours to get the carbon back. So it is not possible that you can put more energy to get carbon than what energy it would have released. So that is where this complete energy balance of carbon dioxide, as Schrodinger equation, it says that 1 volt is 1 electron volt. So to get methane, you will need 8 electron volt for formation of methane. And that is where the major challenge lies. And therefore, whether you go for a methane synthesis as a CO dissociation, CH hydrogenation, OH hydrogenation, and look at the methanol, it's a CHO dissociation. And here it is a coupling. And I'm sure some of you who are in the field of chemical synthesis must be excited about what is the best pathway to get this CO2 reduction to methanol. And if you look at your delta E and look at your turnover frequency, you will realize that copper zinc is considered as the best one. But the problem with all these things, that you are still nowhere near, in terms of your zero, you are bringing down the activation energy. And that is the very interesting observation, that the linear relationship between the bond energy, this is the bond energy of CO2 surface, and activation energy. And what is required, therefore, and this is where I think this is an exciting treasure for a carbon dioxide, is looking at this this particular the activation energy and a CO bond energy. Look at it. I mean, you take platinum, rhodium, silver, copper, they're all in the same line. So most of us, when we publish papers, we look at this line and add some zirconium or add something. Good, I'm not saying one should not do it, but what is required to get into the hill? Because the best TOF you get, the red is good here, so you can see that you can get when you are in the center of this particular region. And that is where I think the whole conventional copper zinc, high pressure, there's a slurry bed or whatever pack bed, we are developing a lot of things. I'm working on a lot of the Indian high ash called to methanol. I'll not go there because I'll be digressing from my work. But doped graphene, and how do you really go away from that scaling and get into the place where you have the lowest activation energy? And that is possible by these kind of molybdenum disulfide or copper zinc in a graphene. And this is the change. If this is the groundbreaking development which can happen for CO2 reduction. I started from 80 electron volt, and when you look at this doped graphene, and there is a lot of active side motives that circumvent scaling. So once you circumvent scaling, and that is something which I hope I am just giving a glimpse of what is in store when you talk about carbon conversion. I talked about carbon capture. Carbon conversion is the next challenge, and that is where this beyond two-dimensional, more functionality, inspirational enzymes, and integration for homogeneous catalysts is something which is working to happen. I'm sure some of you can work on this. It is nothing less than a Nobel-winning kind of a prize. And we are talking about methanol, ethanol, and CH4. Now, this is the ethanol selectivity. Ethanol is definitely better than any other thing, though I am a chairman of the National Methanol Mission. Methanol has got its own advantages because of the hydrogen getting back from a methanol is a lot easier. We are developing a fuel processor for our automobile e-mobility using fuel cell. And there's a big program that I'm running in IIT Delhi with the Center for Automobile Research in IIT Delhi, where we are developing a program of methanol and then getting back hydrogen on board and pushing it through a fuel cell. But ethanol as an energy density is far superior, and you can see where you can get and what is the material. I mean, you can see here, you can see cobalt, copper, platinum are the areas where you get the best selectivity map. And then, of course, when I said carbon hydrogen splitting, can you split carbon hydrogen splitting? That is the ultimate another job that I'm working with with Professor Pant and other people in this one in IIT Delhi. Pyrolysis of methane, where you can just break carbon and hydrogen, and this carbon is such a wonderful nano tubes and composite carbon fibers. This can be used for fabricating the high pressure class 4 cylinders which can carry hydrogen. So instead of CH4 going together, now you use this pyrolysis, carbon is generated. That carbon can be used as a structural material, and all steel structure can be replaced by these carbon structures, which are far superior in terms of the material properties, and that can now carry hydrogen at 700 bar pressure. So methane cracking, looking at a liquid nickel bismuth is another area where you don't have to go to CO2 route at all, and you can get this carbon to hydrogen. So we are looking at some plasma-based systems, and there's a lot of work which I'm doing along with few colleagues in IIT Delhi on this area. So I'm coming to the concluding part of my thing, integration of renewable hydrogen with CO2. 4 pathways that we are looking at. One is a hydrogen generation from a renewable energy, allowing the hydrogen to go by using carbon. But this is the pathway that I'm saying, that capture carbon dioxide from a point source, from a power plant, from steel plant and everything, convert that to using SOEC, using water and carbon dioxide. Of course, do we have a better pathway than SOEC for simultaneous reduction? I think some of you can look at it. I'm sure some of you have got something already. You will look at your periodic table, and you can pick up what is that particular thing, chemistry, which can give me, rather than going to an electrochemical process, can you go for a simple ambient process, which is self-catalytic, autocatalytic, and then convert that into methanol as a very simple, or there also, as I said, graphene, molybdenum disulfide can be a much better way than pressurizing, and then you get your methanol and then do a fuel reformer, fuel cell. So this is the pathway that we are looking at it. We are also integrating that pathway with a high efficient coal gasification pathway. Coal gasification is one area where I've dedicated my 10 years of precious life from 2004 onwards, when I joined from atomic energy to NTPC. Time of coal has come, like Victor Hugo said, you cannot deny an idea whose time has come. Fuel cell, hydrogen, and coal gasification and of course renewable PV are the four important halts. And later on, after 2050, then of course you can use carbon dioxide as a carrier of hydrogen, because that is a much better carrier than even ammonia or many other parts. And that is what we are going to be doing. And metal organic framework becomes one of the other way, where in the fuel cell, if you are using ethanol as a fuel, carbon dioxide can be captured, and that pure carbon dioxide can be done. So my dear colleagues, I'm coming for a question answer session. So road for achieving financial self-sustainability is looking at carbon emitters and looking at carbon dioxide users. So I've given all the pathways: fuel pathway, oil pathway, bulk chemicals, fertilizers, and of course, I don't want to eliminate CO2 sequestration. If you want to reach less than 460 ppm, sequestration is going to be essential. Carbon conversion is going to be essential. Low energy conversion for capture is essential. Getting hydrogen is essential. So all these forms a part of it. Biological processing is extremely important. And you can see today, people are using some activity like a industrial hemp, or growing a hydroponic system where you can capture carbon dioxide and convert that into biologically into a system where you can get those things and use your splitting mechanism of a nickel, so that you get carbon pyrolysis and you get your hydrogen. And that carbon is a very precious carbon because it is in graphitic in nature. We have to see whether, of course, you may not get a graphitic nature from a biological system, or a cellulose or a lignocellulose. But if you are able to monitor them, like in sorghums or in hemps or in bamboos, we can actually look at this option. So there are all infinite options that are available. So we need multiple sciences here. Chemistry is the formation, is the important thing. Electrochemistry is the other part of it. Material science is part of it. Biology is part of it. And a whole lot of engineering developments are required, because there are big developments in material science, chemicals and process integration, intensification, rapid prototyping. So we need multiple disciplines. It reminds me, my dear, at the fag end of my career, this is the fifth career that I'm doing it from my BRC days, atomic energy in 70s. Thrust was given to collaboration models. So I'm only pleading with all of you, and that's where through my dear friend Vivek and Satyanarayana, that we must use this to actually drive a lot of collaborations, industry, academia, and institutions. I'm developing some model for carbon capture center of excellence with the CSIR and interested scientists. We are looking at academic institution to set a center of excellence, and this should not remain as a center with the only deep-rooted R&D, which I've indicated to you, graphene conversion to a dope graphene, or looking at a CO2 or co-electrolysis to a where to lead to a demonstration project. And this is the network that I'm suggesting to government India. We need a lot of innovation hub outcomes, industry, society, R&D expertise, and that is going to be essential in our development. Collaboration, academia is something which I bring, because that has been my mantra from the initial days. And I will conclude this by saying a quote from Atharvaveda, that we must learn to happily progress or together or miserably perish. I think that's the only way human beings can work. We cannot work in silos. We cannot live, or we cannot survive in silos. Man can live individually, but can survive only collectively. Thank you very much. And now hand it over for a question answer session. Thank you.
Thank you very much, Professor Ramakrishna Sonde. I think it was very exciting. You tried to review almost every possible ways of combating the climate change in just 45 minutes. So thank you very much. And now the topic is open for questions.
Yeah.
Okay, maybe I can start.
Can I ask a question?
Yes, Rishi, go ahead.
Thank you. So thank you, sir, for giving this excellent talk. It was very much useful for a student like me who is trying to work in this field. So I have one question regarding the methane pyrolysis that you mentioned. So you mentioned that when we do methane pyrolysis, one can use the carbon which is produced in making things and using it as a building material. So one of the challenges that when the carbons are formed, they usually deactivate or hamper the material or the catalyst that you are using. So as a just a thought that why we need to do a pyrolysis of methane, and why can't we just use the methane as fuel, and then the CO2 which is formed, we can again convert it into methane and close the cycle there only.
No, Rishi, I mean, that's something which I thought I've said, because the moment you are in a you are in a zero-sum game. You are in a cycle. You generate CH4, get CO2, get CH4, again burn it. So there is no way you are capturing CO2. In that case, it's a it can happen once you have removed all CO2 in the atmosphere. Then only that cycle can work. Otherwise, if there's a fresh CO2 which is coming, and that has to be converted into methane by some hydrogen, then somewhere that CO2, that CH4 has to be stored, or CO2, CH4 cannot be further burnt. There is no way that you can convert. The moment you burn CH4, you are getting CO2. Then what do you do with the fresh CO2? So you are into a infinite loop if you don't have that CH4 and don't use that CH4 for any other purpose. The moment, and you can't just keep that CO2 built. I mean, 600. I mean, as I said, 40,000 million tons would mean easily about 20,000 million tons of carbon methane. What will you do with that? So you say burn it. The moment you burn it, you'll get CO2, and that CO2, what will happen to the fresh CO2? So you are not doing anything. So essentially, what you are saying is that don't do that. The moment you extract energy, moment you break the bond, then you get the energy, but then you get CO2. Rather than that, if you can get your carbon, and of course there are many things you said that I will deactivate, and therefore we are using a bismuth, you are losing a nickel. I'm not going to give a big talk. Maybe we can have a separate session on that, because that is one thing which I feel is good. So you get your hydrogen and you get a carbon, and that carbon is an important material because the carbon is a nano material, and it can be used for not building but a structural material. Its properties are 10 times better than hold your breath steel, which steel was touted as, and today steel consumes, every ton of steel generates about 2.6 ton of carbon dioxide. Now, if you don't use steel, you use this composite as your material construction, whether for pressure vessels, whether for structured steel, whether anything can be used carbon, and that carbon can come from methane, and that methane can come from this thermal character, and the hydrogen, now which has got a 33 kilowatt, which has got 3 times more energy than methane, that hydrogen can run your fuel cell. In my view, that is the best pathway. I don't know how much I convinced Rishi on this.
Yeah. I think we're very convincing. Thank you very much.
Thank you, Rishi.
Yeah. So just to follow up with the Rishi's question. So if one can convert CO2 to methane and then burn the methane and get the energy, so ideally, are we not closing one of the inlet of the CO2 emission? Because now I don't need to use the methane from the nature, right? So that methane stays inside. And now I'm only using the methane coming from the excess of the CO2. So one CO2 inlet is closed. Don't you agree with that part?
Yeah, I know, but that is the point that is happening is that to close that you need hydrogen. Now, hydrogen, you have to put some energy. So hydrogen, you are now, if you have to assume that hydrogen will come, because to get that, as I said, 8 electron volts. So you need that hydrogen. Now, hydrogen needs energy. Now, where is that hydrogen coming? Now, either you use SMR, steam methane reformation, to get your hydrogen, because till your renewable energy hydrogen comes, and that hydrogen is so expensive, because today when you talk about a water electrolysis from a solar, the cost of that hydrogen is going to be easily about 700 rupees, or at least $5, Vivek. And because of that, hydrogen is not naturally available. So when you want to convert CO2 to methane, and say that I'm going to be now stopping methane from using, but you're using hydrogen, which again may be coming from methane again. So therefore, somewhere methane gets into the system. If you say that unless you renewable energy becomes a own thing, but that will happen. I'm just talking about next 2 decades. We are into this conundrum of where do you get your hydrogen and what do you do with your methane?
Yeah.
I have just one question. So I just saw this flow chart where you said that CO2 will get converted to CO, then it convert to methanol, then it convert to, we can use it like further conversion, and we can ultimately use in the fuel cells, right? If I'm not wrong. So
Yes.
I was just thinking, why we can't just stop at the methanol level? Why can't just be used as a fuel and just do from go further from there only? Why we need further process?
No, methanol, when you get methanol, you have to convert, extract energy from methanol, isn't it, Saideb?
Yeah. That is why I was thinking how we are extracting. Yeah.
So the methanol, to get energy, best energy conversion of methanol will be via fuel cells, then burning it into a boiler.
Okay.
That's
So
the reason that you call methanol, one, maybe whatever is required for chemicals you use it, but rest of the methanol, Saidip, will have to be acting as a hydrogen carrier. I'm calling methanol as a little low carbon, but a hydrogen carrier. And that is why that particular hydrogen carrier can be, you can get back hydrogen almost about 83% efficiency. We have developed this methanol reformer, and that hydrogen will now generate a power at a much higher efficiency than what CO2 would have done. And that is the magic of this whole thing. That means you take your CO2, reduce it to CO, get your hydrogen, get your methanol, and that convert back. But then it gets into CO2 again. So the way that CO2 you have to handle it is that whether either you capture it in the form of a metal organic framework, or you have to allow that CO2 to be again captured by your hydrogen, what Rishi now talked. But I said in that process, the whole thing you are in a zero-sum game, and that is not going to solve the whole thing. So you will have to look at it from that angle, Saidi.
Okay, thank you. Yeah.
Thank you.
Ashish, you want to ask the question that you wrote?
Right. You can read it for me, not Rishi.
No, go ahead, Ashish. Yes.
Yeah, it was a wonderful talk. Is there any possibility of having a single pot CO2 capture as well as conversion together to any fuels or product? If at all there is any possibility, can you comment on what products one can focus on?
Well, I really only feel that biological way is the only best way that you can capture it, Ashish, because nature we have to follow. If you are able to follow the nature, and if you are able to take whatever may be the quality of for this thing and use your photonic, I mean, you know, all that black and dark, dark and light reactions and how this whole thing. So the only pathway that I still feel that you use a carbonic anhydrase as an enzyme and get that, because then it is not bothered about whether SOx is present, NOx is present, particulate matter is present. It can be used as a brute force, convert that into anhydrase, and then you can grow. And that is where I was talking about this kind of a vertical growing of your hydroponics using hemp as a very fast growing trees. And then you can get that particular biological mass converted into biological mass directly at a rate at which you're generating. Because as I said, even a single 220 megawatt plant, which I have been working when I was in NTPC, can generate about 140 tons of carbon dioxide, which is whole chemicals of carbon dioxide can be made by one single plant. Whereas we have got now such 1,000 such plants, and therefore biological way would be one way of doing it. The other way could be, I know that there's a lot of research which is happening. I mean, if you can look at some of these magnesium carbonates or calcium carbonates or whatever, that direct air, and assuming that there's enough lime which is present, and that lime can be sequestered terrestrially rather than in a geological mineralization, if you are able to accelerate the process or use some electrical conversion back to magnesium or this one. There are a lot of work, but I'm not familiar with that work. But biological process, take it from me, Ashish, will be the most sustainable process.
Thank you. Thank you for your answer.
Rick, there is a question from, 1 minute, let me see if he is there still on the call. Okay, I don't see him, but
On YouTube, you're saying?
yeah, no, it is in the Zoom. This is Professor Dheeraj Patil, IIT Dharwad. Are you there on the call?
But anyway, question can be asked for the benefit of others.
Okay, I'll read question for you.
Sure, thank you.
How much experimental and simulation methods have been put to use so far for the mixing and burning of H2 plus natural gas?
Oh, a lot of work has happened on this, Professor Satyanarayana. A lot of work has happened. In fact, IIT Delhi, Mahindra had developed an entire program in about 8 years back. There is a group of people who are working. So we had set up a internal combustion engine using this methane and what we call hythane. It used to be called as hythane, hydrogen, and natural gas. And a lot of not experimental work, a lot of CFD has been done, because there's a challenge to make a CFD there in terms of the reaction kinetics. But in terms of the experimental setup, work has done. My colleague in IIT Delhi, and there's a group of people in IIT Delhi, along with Mahindras, have submitted. But I really do not know final advantages of how much efficiency increase it has happened, how much reduction in carbon dioxide has come. In fact, I feel that today fuel cell, I don't know, maybe I'm a little biased. Fuel cell is the best way rather than doing this mixing, but that may still be an interim arrangement for next 2-3 years, because a lot of work has happened. But then to carry methane on one cylinder and hydrogen on another cylinder and putting that into an engine may be difficult, and therefore automobile companies are also lost their interest in using this directly. Satyanarayana.
Okay, so that is a question, of course, from Professor Dheeraj Patil from IIT Dharwad. Another question that I'm going to ask is by one Abhinav Chaudhary, participant from YouTube. How polyoxometalates are used as electron and proton reservoir, which assist in electrochemical carbon dioxide reduction.
Hello.
Yeah, could you hear me?
Yeah. Can you say repeat again? I missed you for a while, for a short while. I missed you.
Yeah, the question is from Abhinav Chaudhary from YouTube. It says how polyoxometalates are used as electron and proton reservoir, which assist in electrochemical carbon dioxide reduction.
I have no idea. In fact, I must confess that I heard something of this metal oxo ions, but I really do not have any idea as to how they work and what kind of a thing that can happen. Maybe.
Oh, okay.
I would like to pass this question.
Sure. I think there is one more question from Professor B.M. Jaffer. Are you there on the call, please? Okay. Otherwise, I'll read this question for you. Algae present one of the fastest CO2 sequestration system. We tried for finding unsuccessfully for algae fountains, air purifiers, etc. Any comment in promoting this technology?
No, we should promote this algal conversion. It is very potential. I know that a lot of work is required. It's not a common, because it's a synthetic biology. How do you really engineer a algae to develop? There are a lot of varieties, blue algal nature, and there's really a good team which is working in a private sector. They are really working on this. Now, algae as an air purifier is a very different thing, because that's a different kind of a thing, because what you want to purify there is not carbon dioxide, but the purification is respect to the particulate matter. And there's a different kind of a thing where you use a biological species to capture SOx's, NOx's, and some of it. But the carbon dioxide capture to accelerated photosynthetic biology is a deep science. I think there's a lot of work which is happening. I'm talking about the hydroponics. I'm talking about even algal development, and both the developments are potent enough, and enough work is happening how to really accelerate this process of capturing. So that, but only thing is that after hydrogen, what you do, or after algae, what you do with that particular algal mass, because algal mass is going to be a rate of generation of CO2. If this is matching, then if you assume that I'm going to be capturing 2 million tons, and 2 million tons of algal mass will have to be captured, and then you have to use it for some purpose, because you can't just dump it in one place. And that is where this, what I was talking earlier about the pyrolysis, plasma pyrolysis will be the best way to get the carbon and hydrogen and don't go to a CO2 cycle, unlike you take methane and burn the methane. So that's a very interesting pathway, and a very, very credible pathway at that. Yeah.
The question from...
Thank you, sir, for that interesting comment.
Okay. So that was Professor B.M. Jaffer. Yeah. Another question from Professor Vivek Datar this time. I think he's going to ask it.
Maybe it's a naive question, but I wanted to ask, what is the future of carbon in structural materials? At what rate is it rising right now? Is it kind of, can one hope that, it will be almost equal to steel and other structural materials in the next 10 years or so?
Well, you are right. I think there is some audit one has to do, because as you're talking about a green cement, green steel, people have been also looking at a green cement and looking at carbon dioxide to be used as a capture. In fact, a lot of these building materials or the structural materials which are using pouring concrete, going away from Puzolona and various things, is being considered as a good sink for carbon dioxide. But I really do not know what kind of a mineralization chemistry works there. But Vivek, I can come back to you on this. Right now, I have limited understanding that it acts as a sink, but how much of it and what percentage, I simply don't have numbers on my fingertips.
Okay, thank you.
So Vivek, do you want to continue further? Vivek.
I said you mean Vivek Polshettiwar.
I'm sorry, sir. Two Viveks on the call. Yeah. Vivek Polshettiwar, do you want to continue anything on this? We can't hear you. I don't know if you're.
Oh, sorry. Okay, I was muted, I think. Yes, Satyanarayana, so you go ahead now.
No. I mean, I just took a call. If any other questions or.
Yeah, if we have any more question, please raise your hand. Then we can have a further discussion.
May I ask one comment, please?
Yes, Professor Ali.
Sir, we are talking about fixing this carbon dioxide in terms of carbon from the excavating from the fossil fuel on the surface. On a long-term basis, what can be an ecological impact of huge carbon dioxide sequestered but deposited on the surface? You think whether we will miss the bus of its impact on ecology?
Professor Jaffer, really, I don't know. A lot of work is still happening. I told you that to sequester CO2 permanently requires a huge mineralization chemistry. Now, when you talk about kaolin or you talk about feldspar, the sedimentary rock, lot of work has happened only in a numerical way or in a kind of on a desk table. This work has been done. But in terms of really what kind of a mineralization, what kind of a CO2 will remain as a mineralized and how much of it will remain as a independent, still unsequestered, supercritical, Jafar Saab, it is still not been done very well. But my own understanding is that as long as you have got a sedimentary rock, which has got an aquifer, and on top of it, there's a cap rock so that it will not allow carbon dioxide to escape from that particular system. I think I mentioned that in my thing. And there are few places in the world, there are beautiful sedimentary rocks which can really kind of take care of the carbon dioxide permanently into its womb so that it will not come out. But if you ask me, what is your probability that it will not come out? I wouldn't say that it's 100%. So that is a risk that one has to understand, that when you put them under the geological formations and allow that for hundreds of years or millennia, it will remain there, is your guess is as good as my guess. Now, you're talking about on the surface, on the terrestrial side, when you want to do it, again, terrestrial side is much easier because you can keep them monitoring it. Of course, you can monitor also the deep sedimentary rock, but on the terrestrial side, when you want to do it, like you do it in the cements, or you can do it in the building materials, or in the road construction, because there are a lot of people who are coming. CRRI of CSIR is also coming to me whether we can use it as a carbon sink. They are possible, and you can monitor them, and you can in fact accelerate the chemistry by some of the additives and binders, so that you can actually ensure that the carbon dioxide will not release back into the atmosphere. Certain amount of modeling has been done to ensure that there's a permanent burial of carbon dioxide when you sequester. In fact, oceans would have been the best way to store carbon dioxide. But obviously, I think many of you will pounce on me saying that no ocean, because it will change the complete pH and chemistry of ocean, and ocean is a treasure. Ocean sustain the entire Earth balance structure. So you cannot use ocean as a storage. You cannot use of course, growing forest is always a good thing. That's what I'm saying. Growing forest or artificial forest like algal and hams and other biomasses is another one, but the rate will not be matching. So mineralization will become another important criteria, either deep or on the surface. Have I answered your question?
Yes, sir. Thank you, sir. Actually, I started teaching carbon sequestration this semester to our students. Your talk was wonderful, a lot of eye-opening for me. But only small reservation from personal research is that I thought sequestered carbon converting into biofuel is the mantra and going to be boom in the research activity, whether it is 2D material or any other carbon sequestering material. But you made a point of caution that let's go to a cycle where carbon sequestration is lasting rather than converting them into immediate biofuels and exploitations. So I have to sink this point very hard in my mind. and see what best can be done in terms of imparting this knowledge to students as a modern research direction. Thank you very much for your valuable
Hold
time.
hand, I'm saying this. I will send you my all equations, my calculations. You are in a zero-sum game. You capture it and you release it, capture it and release it. You feel momentarily that you have solved the problem, but you have actually not solved the problem. I can send you all my publications, why it is foolish to convert this. Sorry for using this word again, because somebody...
I got it, sir. I'm really impressed. I got your point.
But it will not work, sir. That's why I'm saying.
Thank you very much, sir, for the input.
Thank you.
Okay, so if there are no more questions, thank you very much, Professor Ramakrishna Sonde. It was really exciting talk, and hopefully we'll interact more on 15th July during the launch symposium of CO2 India. So thank you very much again, and thank you everyone for attending the colloquium.
You can share my presentation, Vivek, to everybody. There is nothing, no rocket science in whatever I've done. So whoever wants it, you can share it, and it is available open for this thing, and we will have a separate discussion. So Satyanarayana, thank you very much for giving me the opportunity, and Vivek more particularly, that yes, we'll continue this dialogue. Hope this becomes a harbinger for next dialogue. Thank you so much. Bye.
Thank you. Thank you very much, sir. Thank you, Professor Ramakrishna Sonde. Also, of course, Vivek, for making this very, very interesting, and a lot of discussion that happened. I think it's a lot of what you call takeaways from this particular colloquium. And once again, thank you very much on behalf of all of us, both TIFR and ASSET colloquium.
Okay. Bye-bye. Bye-bye.
Thank you so much.